There are some problems in the AP Calculus exam that make us convert these sigma notation limit Riemann sums into integrals. And we have to be able to interpret what this limit actually means. So first of all, what is an integral? Okay, so an integral can be thought of a small but the sum of a bunch of small rectangles from some starting point x equals a to x equals b, and those rectangles are going to be made by multiplying the height of the function times dx. So one of the keys to interpreting the sigma notation is that we want to figure out what part of that notation is our dx part of that notation. So our dx part of that notation is going to be the interval width, so how far from left to right, divided by the number of intervals. So it's going to be the interval width I divided by n. So that's going to be our dx. So our dx in that expression is that part that I just shaded in green. We also need to find the part of that expression that represents the x variable. And that's going to be found by the interval width times the k over n. Okay, so the k represents the steps, okay, how many steps we have divided by n. So if we have at our 0 step or our first step, we're going to have the interval width times 1 divided by n. So that's going to give us the x portion of that. If k is equal to n, then we're going to be at the end of that interval width. Okay, so k and n, if they're equal, that means we're at the end. That means we're going to be at the end of the interval width. Okay, so this we're going to add to this expression, but in general, that part's going to be our x variable. So if you can take a look at the original sigma, this portion then represents the x variable of that expression. And the last part is we just need to establish what is the bounds, the starting point A, what is the x value at the starting point, and what is the x value at the ending point? Well, we can establish that by substituting in our k and n, okay, and we can establish our start and end values. But now we have to be aware that our n now, we are doing a limit. So that limit, n is going to infinity. So we're going to end up dividing by infinity. So we're going to end up with some finite k value divided by infinity. So that's essentially going to be the 0 starting point. And then when we have k equal to infinity divided by n is infinity, we're going to have the interval width as our x value there. Okay, so we're going to add on a piece here to that k value, to the x value, some portion here later on, but for now we're just going to assume that we're going to start at 0. So we plug in our k over n is our expression. We start at 1, k equals 1 and n is infinity, so it's going to give us 0. And when k is infinity, n is infinity, that expression, k over n expression, is going to be 1, which is then going to leave us with that interval. If we take a look up here, that will just leave us with the interval width as our x values that we're using. So how do we then establish what the f of x function looks like? Well, we can just, as long as we can pick out the x part, the dx part, the rest of it then must be the f of x part. So in this case here, we're going to have, if we tease out the k over n, right, this part here that I've highlighted in blue, that represents our x. The green represents our dx. Well, then we have the f of x times dx part of that expression. So we end up with this piece that looks like this. So we end up with our f of x, okay, when we replace the k over n, ki over n with the x, and then we replace the 1 or the interval width divided by n with the dx part. We plug in k equals 1, n is equal to infinity. That gives us our starting value. So in this case, our starting value is going to be 0. Okay? And then when we plug in if k is infinity, n is infinity, we'll get our ending value. In this case, it happens to be 1. So there is our sigma notation, how we convert that sigma notation into our integral notation. Okay, so in this case here, from k equals 1 to infinity, we're just going to go from 0 to 1. Okay, now we'll show how we can change that up in the next example.